You know that feeling when you're completely lost in something, maybe a good book, and hours just disappear?
Oh, definitely. Or the opposite, right? Stuck in traffic and 5 minutes feels like an hour?
Exactly. It feels like time is, I don't know, flexible. But the really wild thing is, in physics, it actually is. Okay, let's unpack this. Today, we're doing a deep dive into something huge, Einstein's theory of relativity. And we're zeroing in on maybe the weirdest part-time dilation.
What's fascinating here is, yeah, it sounds abstract, but it fundamentally changes how we see, well, everything,
Yeah.
space, time. It makes you question what's really fixed in the universe. So our mission today is to explore these core ideas, especially how time can stretch, look at some really cool experiments that proved it, and see how it affects tech we use every day. We'll even touch on the bigger philosophical questions it raises.
And where are we getting this info from?
We've got a good mix: university physics texts, some historical accounts of how these ideas developed, key scientific papers, even lecture notes. A pretty solid foundation.
Great. So, to really get Einstein, we kind of have to start before him, right? Maybe with Galileo.
Yeah, absolutely. Galileo set some important groundwork. Think about his ship analogy.
Right, the one where you're below deck.
Exactly. You drop a ball, it falls straight down. Simple enough. Now the ship's moving, but smoothly, constant speed.
Okay.
You drop the ball again, and it does exactly the same thing. Falls straight down relative to you and the ship.
Because everything's moving together. The ship, you, the air, the ball, it's all one system.
Precisely. That's an inertial reference frame. As long as there's no acceleration, the basic laws of physics seem the same, whether you're still or moving.
Makes sense for dropping balls. But then things got complicated later on, especially with light.
That's the crux of it. Fast forward to the 1800s. Scientists are digging into light, electricity, magnetism, and they hit a snag. Experiments like the famous Michelson-Morley one, trying to find this aether stuff they thought light traveled through, kept finding something really odd.
What was that?
The speed of light, it always measured the same. Always. Didn't matter if you were moving towards the light source, away from it, or if the source was moving. It was constant.
It's weird, right? If I throw a baseball from a moving car, someone on the ground sees it moving faster than if I just threw it standing still.
Exactly. That's classical thinking. But light just didn't play by those rules. Its speed in a vacuum was this absolute constant, about 300,000 kilometers per second. And that just didn't fit. It was a major puzzle.
Okay, so enter Einstein. What was his big idea?
Well, instead of trying to explain why light behaves so stubbornly, Einstein basically said, okay, let's assume it's true. Let's take it as a fundamental rule of the universe and see what happens.
Bold move.
Totally. And he built his special theory of relativity on two core ideas, two postulates.
Okay, what are they?
First, the laws of physics are the same for everyone who's moving at a constant velocity in those inertial frames we talked about, basically building on Galileo.
Right. And the second one?
The second one, and here's where it gets really interesting, is that the speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer.
He just accepted the weirdness.
He accepted it and made it a foundation. And from those two seemingly simple ideas flowed some truly mind-bending consequences about space and time.
Like time dilation. Let's get into that. What does it actually mean?
Okay, so time dilation basically means that time intervals can appear different depending on who's measuring them, specifically based on their relative motion. Time can stretch.
How does that work? The light clock thing helps here, right?
Yeah, the light clock is a great thought experiment. Imagine you're an astronaut inside a spaceship. You've got a clock made of a light pulse bouncing between two mirrors, one on the ceiling, one on the floor. Tick-tock, up and down.
Okay, straightforward for the astronaut.
Right. For them, light travels a simple vertical distance. But now, let's say I'm watching your spaceship zoom past Earth at like half the speed of light.
Okay, you're the earthbound observer.
From my perspective, as the light pulse travels from the floor to the ceiling, the ship itself has moved forward. So I don't see the light going straight up and down. I see it traveling a longer diagonal path.
Ah, because the top mirror moved while the light was in transit.
Exactly. Longer path.
Yeah.
Now, remember Einstein's second rule.
The speed of light is constant for everyone. For me on the ship and for you on Earth.
Precisely. So if you see the light travel a longer distance, but its speed is the same for both of us, what does that imply about the time it takes?
It must take longer from your perspective on Earth.
Bingo. Your tick takes longer from my point of view than it does from yours. Your time, as I observe it, is running slower. It's dilated.
So the time the astronaut measures right there with the clock, that's special somehow.
Yes, that's called proper time. It's the time interval measured by an observer for whom the start and end of the event, in this case, the light hitting the mirrors, happen at the same location. It's always the shortest possible measured time between two events.
And anyone moving relative to that clock sees the time interval as longer dilated.
Correct. It's stretched out from their perspective.
Is this just like an optical illusion or how we perceive things?
No, that's the crucial point. It's not an illusion or a measurement trick. Einstein's theory says that dilation of time is an intrinsic property of time itself. It's real.
So all clocks moving relative to me would appear to run slow, even biological ones, like aging.
Yes. Your heartbeat, chemical reactions, the whole process of aging, anything that marks time, would be observed to proceed more slowly in a frame moving relative to the observer compared to a clock stationary relative to them.
But we don't notice this day to day.
Right, because the effects are absolutely minuscule at everyday speeds. Even for something incredibly fast by our standards, like a hypersonic jet, the difference is tiny fractions of a second per second. It's practically nothing.
But it becomes significant when
When you get close to the speed of light. As velocity increases, the time dilation effect gets much, much larger. Dramatically so.
Okay, so it's a wild theory, but is there actual proof? Not just thought experiments.
Oh, absolutely. Fantastic experimental proof. One of the classic examples involves particles called muons.
Muons.
What are they? They're subatomic particles, kind of like heavier electrons. They get created way up in the upper atmosphere when cosmic rays, high-energy particles from space, smash into air molecules.
Okay, created high up. What's special about them?
They're incredibly unstable. They decay very, very quickly. When they're at rest, their average lifetime, or half-life, is just about 1.5 microseconds. Tiny.
So 1.5 microseconds, they're created maybe 10, 15 kilometers up. They wouldn't make it down here, would they? Traveling even near light speed.
Exactly. If you just use classical physics and their known lifespan,
Yeah.
you calculate that almost none of them should survive the trip to reach Earth's surface. They should decay long before they get here.
Do we detect them?
We detect loads of them, far more than classical physics would ever predict.
So why? Relativity.
Relativity. The muons are traveling incredibly fast, very close to the speed of light. From our reference frame here on Earth, their internal clocks, their decay process, are running much slower due to time dilation.
Their 1.5 microsecond lifespan gets stretched out from our perspective.
Massively stretched out. It gives them enough borrowed time, from our view, to actually make the journey down to the ground before decaying. The number of muons we detect matches the predictions of special relativity almost perfectly. It's incredibly strong evidence.
Wow, that's compelling. Any other big experiments?
Definitely. The Hatfield-Keating experiment in 1971 is another famous one.
What did they do?
They took super accurate atomic clocks accurate to nanoseconds, put some on commercial airplanes and flew them around the world, once eastward, once westward. Then they compared the time elapsed on the traveling clocks with identical clocks that stayed put in their lab. And they found tiny but measurable differences in the elapsed times. Differences that matched the predictions of both special relativity, due to the plane speed, and actually general relativity, due to altitude differences, which we'll get to. It showed these effects happen to real macroscopic clocks, not just weird subatomic particles.
Okay, this leads into that famous idea of the twin paradox, right?
Ah, yes, the twin paradox. It's a classic consequence of time dilation.
So the setup is, one twin stays on Earth, the other zooms off in a spaceship at near light speed, travels around, and comes back.
Right. Let's say the traveling twin goes out at a speed where time slows down significantly for them, maybe by a factor of 30. They experience, say, 2 years on their trip, according to their clocks and calendars.
Okay, 2 years for the astronaut.
When they return to Earth, because time was running slower for them relative to Earth, they'd find that much more time has passed for the Earthbound twin. If the factor was 30, then 2 years for the traveler means 60 years have passed on Earth.
60 years. So if they were both 40 when the trip started.
The astronaut returns, age 42, but their twin on Earth would be 100 years old, assuming they're still around, of course.
That's mind-bending. But here's the paradox part people talk about. Couldn't the astronaut say, hey, from my perspective, Earth was moving away and then came back, so should that the Earth twin be younger? Why isn't it symmetrical?
That is the absolute key question, and the resolution lies in realizing the situation is not symmetrical.
How so?
The Earthbound twin stays, more or less, in a single inertial reference frame. They aren't accelerating significantly.
Yeah.
But the astronaut twin, They have to accelerate violently to leave Earth, decelerate to turn around, accelerate again to come back, and finally decelerate to land.
Ah, they change reference frames. They feel forces. The Earth twin doesn't.
Exactly. The astronaut undergoes acceleration. They are in non-inertial frames during parts of the journey. That breaks the symmetry. It's the twin who undergoes the acceleration and turnaround who experiences less elapsed time.
Hmm.
There's actually no paradox when you account for the acceleration and the change in frames.
Okay, that makes sense. Acceleration is the key difference. So this isn't just sci-fi fuel, it actually matters. You mentioned GPS.
Hugely important for GPS. The Global Positioning System relies on a whole constellation of satellites orbiting Earth, each carrying incredibly precise atomic clocks.
And they all need to be perfectly synchronized, right?
Yeah.
For us to figure out our position.
Perfectly synchronized. And we need to know exactly how fast their clocks are ticking relative to ours down here on the ground. And relativity plays a massive role in that.
Wow, both kinds of relativity.
Both kinds, yes.
Yeah.
Special and general. First, special relativity. Those satellites are whipping around the Earth at about 13,000 kilometers per hour. That's fast.
So time dilation should make their clocks tick slightly slower than Earth clocks.
Correct. According to special relativity, due to their speed, the satellite clocks should lose about 7 microseconds per day compared to clocks on Earth.
Okay, 7 microseconds slower. But you said general relativity too.
Right. Now, general relativity, which deals with gravity. The satellites are orbiting high above Earth, about 20,000 kilometers up.
Where gravity is weaker than on the surface.
Weaker gravity. And general relativity predicts that clocks run faster in weaker gravitational fields. So because they're higher up, the satellite clocks should actually gain time compared to Earth clocks.
Faster? How much faster?
Quite a bit more, actually. This effect makes them run faster by about 45 microseconds per day.
Okay, wait. Special relativity makes them 7 microseconds slower. General relativity makes them 45 microseconds faster. They work in opposite directions.
They do, but they don't cancel out. You have a net effect. 45 faster minus 7 slower.
Means the satellite clocks actually run faster overall by about 38 microseconds per day.
Exactly, 38 microseconds faster each day, and the GPS system must account for this difference. If it didn't, those tiny errors would accumulate rapidly.
How bad would it get?
Positioning errors would grow by about 10 to 12 kilometers every single day. The whole system would be completely useless within hours.
Wow. So every time I use Google Maps or Waze,
You are directly benefiting from calculations that precisely correct for Einstein's theories of relativity. It's relativity in action, right in your pocket. There's also another correction needed for the Signac effect due to Earth's rotation, but the SR and GR effects are the big ones for clock timing.
that's incredible. So you mentioned general relativity handles gravity. How did Einstein move from special to general?
Well, special relativity was brilliant, but it only applied to those non-accelerating inertial frames. It didn't include gravity. Einstein spent about 10 years grappling with how to incorporate gravity and acceleration into his framework.
And a breakthrough was the equivalence principle.
That was a key insight, yes. The equivalence principle. It basically states that locally you can't tell the difference between being in a gravitational field and being in an accelerated reference frame.
The elevator
An
analogy.
Osic elevator analogy. If you're in an elevator in deep space, far from gravity, and it starts accelerating upwards constantly, you'll feel pressed to the floor, just like you feel weight standing on Earth due to gravity. Conversely, if you're in an elevator on Earth and the cable snaps, you and everything inside will be in free fall. You'll feel weightless, just as if you were floating in space with no gravity. So locally, acceleration and gravity feel the same.
So gravity isn't a force pulling things. What is it then in general relativity?
It's the curvature of space-time.
Yeah.
That's the revolutionary idea. Mass and energy don't create a force of gravity. They actually warp or bend the fabric of space-time around them.
The rubber sheet analogy comes up here, right?
The helpful visualization, yeah. Imagine space-time as a stretched rubber sheet. You place a heavy ball like the sun onto it, it creates a dip, a curve in the sheet.
Okay.
Now, roll a smaller marble like Earth nearby. It doesn't get pulled by the sun directly. Instead, it follows the curve in the rubber sheet created by the sun's mass. It orbits because space-time itself is curved.
So planets orbit the sun because they're following the curves in space-time the sun creates. Even light follows these curves.
Exactly. Even light, though it has no mass, travels through space-time, so its path is bent when it passes near a massive object. That's gravitational lensing.
And the space-time, it's really 4 dimensions, 3 of space and 1 of time merged together.
That's the picture general relativity paints, a unified four-dimensional geometry. And time is treated as a dimension, interwoven with space. It's not just a separate parameter ticking away independently.
You mentioned light cones earlier in this context.
Right, light cones help visualize the causal structure within this 4D spacetime. From any event, a point in spacetime, the light cone represents the boundary of cause and effect.
How so?
Anything inside your future light cone is a point in spacetime you could potentially reach or influence, because you'd need to travel slower than light. Anything outside is causally disconnected, for now you can't get there, or affect it without exceeding light speed, which is impossible. The cone surface itself represents the path of light rays.
And proper time fits in here too.
Proper time, that shortest time interval we talked about, is essentially the time ticked off by a clock moving along a path inside the light cone, what we call a time-like trajectory.
It all sounds incredibly complex mathematically. How do physicists actually work with this?
It requires some pretty advanced math, specifically tensor analysis. General relativity is expressed using equations involving tensors.
Tensors. What are those, basically?
Think of them as mathematical objects that describe physical quantities in a way that doesn't depend on the specific coordinate system you're using. They handle how things change when you switch perspectives or warp spacetime. The most important one is the metric tensor.
What does that do?
The metric tensor, usually written g-nu-nu, essentially tells you the geometry of spacetime at every point, how to measure distances and time intervals, taking the curvature into account.
And Einstein developed equations using these.
Yes, the Einstein field equations. They are the heart of general relativity. They precisely relate the distribution of mass, energy, momentum, pressure, everything on one side of the equation to the curvature of spacetime, represented by tensors derived from the metric, on the other side.
So stuff tells spacetime how to curve.
And spacetime tells stuff how to move. That's the essence of it.
And we know these equations work because
Their predictions have been verified incredibly accurately. The tiny precession of Mercury's orbit that Newtonian gravity couldn't explain, the exact amount light bends around the sun during an eclipse, subtle effects on clocks at different heights, and most dramatically, the direct detection of gravitational waves from colliding black holes and neutron stars by LIGO and Virgo. These waves are ripples in spacetime itself, predicted by the equations.
Speaking of dramatic, EMC fits in here somewhere too, right? How does that relate?
EMC comes from special relativity initially, but it's fundamental. It shows mass and energy are equivalent, interchangeable. It also has implications for speed limits.
Oh, so
As an object with mass accelerates closer and closer to the speed of light, its relativistic mass, or inertia, increases from an outside observer's perspective. To reach the speed of light, its mass would become infinite, requiring infinite energy to push it further.
So nothing with mass can ever reach the speed of light. It's the ultimate speed limit.
The cosmic speed limit, exactly. Only massless particles, like photons, light particles, can travel at the speed of light.
Okay, if we want the most extreme curvature, the most warped space-time, we have to talk about black holes.
Definitely. Black holes are where general relativity really gets pushed to its limits. They are regions where gravity or space-time curvature is so intense that nothing, not even light, can escape once it crosses a certain boundary.
They form from massive stars collapsing.
Usually, yes. When a very massive star runs out of fuel, its core collapses under its own gravity, crushing down to an incredibly dense point or singularity, warping space-time intensely around it.
And we see stuff around them, like disks and jets.
Often, yes. If there's gas and dust nearby, it can get pulled into orbit around the black hole, forming a superheated accretion disk. Friction in the disk heats it up immensely, making it glow brightly in X-rays. And sometimes, powerful jets of particles are blasted out from the poles at near-light speeds. We see these in distant galaxies.
And they bend light, too, right? Lensing.
Massively. They act as powerful gravitational lenses, distorting and magnifying the light from objects behind them. It's one way we can infer their presence, even if we can't see the black hole itself.
The key feature is the event horizon, right? The point of no return.
Exactly. The event horizon isn't a physical surface. It's a boundary in space-time. Cross it, and your future path inevitably leads to the singularity. You can't escape back out, because doing so would require exceeding the speed of light.
But what's it like at the horizon? Is it dramatic if you're falling in?
This is where it gets really counterintuitive. It depends on the observer.
Yeah.
For someone actually falling into a reasonably large black hole, let's call her Alice again, she wouldn't necessarily feel anything special right as she crosses the event horizon. Her watch would tick normally. Space-time locally would seem fine.
Really? Nothing.
Locally, No dramatic effects at the horizon itself for a large black hole. The tidal forces that would eventually tear her apart become extreme, only much closer to the singularity. But for someone watching from far away, Bob, it's completely different.
How does Bob see it?
Bob would see Alice slow down as she approaches the horizon. Her image would get dimmer and redder, redshifted, because the light escaping the intense gravity loses energy. From Bob's perspective, Alice would appear to take an infinite amount of time to actually reach the horizon. He'd never actually see her cross it.
So Alice sails across, Bob sees her freeze forever. That's bizarre.
It highlights how time and observation are relative in these extreme environments. Tools like Penrose diagrams help physicists map the causal structure, what can influence what even when our intuition about distances and times breaks down near horizons.
Okay, so stepping back from the extremes, what's the bigger picture here? The philosophical impact of all this relativity stuff.
It's profound. Relativity forced a major shift in how we think about fundamental concepts.
Yeah.
Things we thought were absolute, like simultaneity, whether two events happen at the same time, turned out to be relative, dependent on the observer's motion.
So truth becomes relative.
Not quite truth itself, but the description of reality can be relative. Relativity shows that many concepts are actually coordinative definitions. They depend on how we choose to measure them, using things like light signals and clocks. There isn't one single true way to assign coordinates or times. There could be multiple equivalent descriptions, different languages expressing the same underlying physics.
And it changes how we see time and causality.
Yes, it strongly links time order to causal order. A cause must precede its effect in all reference frames. That's built into the structure of spacetime via the light cones. Because nothing can travel faster than light, there's a limit on how quickly cause and effect can propagate. This means there can be pairs of events that are so far apart in space and close in time that no signal could travel between them. For these events, the time order isn't absolute. One observer might see A happen before B, another might see B before A, and a third might see them as simultaneous. But crucially, neither A nor B could have caused the other.
So causality is safe, but simultaneity isn't absolute.
Precisely. And interestingly, while relativity makes time order, cause before effect, fundamental, it doesn't inherently define an arrow of time, why time seems to flow only forward. That seems to come from other physics, like thermodynamics.
It really does challenge our everyday intuition about how the world works. It must have been, and still must be, tough to wrap your head around.
Absolutely. And the mathematics needed, especially for general relativity, is quite demanding. Tensor analysis, covariant derivatives, the Riemann curvature tensor, these are sophisticated tools.
That Riemann tensor, what does that tell you?
The Riemann curvature tensor is key. It's built from second derivatives of that metric tensor we mentioned. Essentially, it measures the intrinsic curvature of spacetime. The Riemann tensor is zero, spacetime is flat, or can be made flat just by changing coordinates. If it's non-zero, spacetime is genuinely curved, like near a star or black hole, and no change of coordinates can flatten it out. It's computationally intensive. Physicists joke about indices all over the place, but it's the precise language needed to describe gravitational geometry correctly.
Wow, what a journey. We went from, Galileo dropping a ball on a ship all the way through time stretching, the twin paradox, GPS needing corrections, space-time bending, black holes. It all traces back to Einstein questioning assumptions about space and time.
It really does. His insights completely reshaped physics and our understanding of the cosmos. It showed that space and time are not just a passive backdrop, but dynamic players intertwined with mass and energy.
It's amazing how deep physics reveals the universe to be.
Indeed. And relativity clarified what absolute time would imply a universe where signals could travel infinitely fast, where simultaneity would be absolute. But our universe empirically doesn't work like that. It follows Einstein's rules, where time is intimately linked to the order of causal chains, limited by the speed of light. And it leaves you with a thought, doesn't it? Imagine if the speed of light were much, much slower. Slow enough that the delay in, say, a video call across the country was really noticeable, minutes even.
Okay.
If relativistic effects were part of our everyday experience like that, would the idea that simultaneity is relative feel as strange? Or would it be as intuitive to us as, say, knowing that it's a different time in London than in New York?
Huh. That's a great question. Would we just adapt our common sense to a relativistic reality if it were more obvious? Something to chew on. Well, this has been an amazing deep dive. Hopefully it encourages you, the listener, to keep exploring how these fundamental ideas shape everything around us. The universe is definitely stranger and more wonderful than it first appears.